Can everybody see my screen now? Okay, so the next paper is from Antonio Lima, frequency-dependent equivalent based on idempotent decomposition and grouping. So the presenter is Professor Lima. He received the master and doctor degree in electrical engineering from Federal University of Rio de Janeiro in 1997 and 1999. In 1998, he was a visiting scholar at the Department of Electrical and Computer Engineering, University of British Columbia. From 2000 to 2002, he was with the Brazilian Independent System Operator. Since 2002, he is with the Electrical Engineering Department, Federal University of Rio de Janeiro, where presently he is a full professor and the head of the Electrical Engineering Department.
Hello, everyone. Thank you for being here in our presentation. My name is Antonio Lima. I am a professor at the Federal University of Rio de Janeiro, and I'll be presenting our paper, Frequency-Dependent Equivalent, based on Idempotent Decomposition and Grouping. The authors are myself, Dr. Felipe Camara from Furnas, it's a utility in Brazil, Professor Joao Salvador from Cefet, another university in Rio, and Professor Maria Teresa Correia de Barros from the University of Lisbon. The paper is organized as follows. I first will present a brief introduction of the subject and all the basis of our work. Then I will go to the idea of idempotent decomposition and grouping. Then we move to the frequency domain realization of the fitted, so we can achieve a fitted network. We will present some results regarding the time domain realization of one test cases, and then we move to the conclusions of our paper. This introduction, in power system nowadays, we have to deal with basically these three topics. One is the network expansion, the other one is the environment constraints, and this leads to the increase in the complexity of power system nowadays. And as the power systems are becoming more and more complex, it's becoming more difficult to represent in detail the large networks involved. And typically we deal with a large representation of the network, but just using positive sequence equivalents. And sometimes we add some machine dynamics, but then if we go to a full detailed representation in phase domain of overhead transmission lines, transformers, and all the components involved, it can become a very large system, and we may lead to unfeasible simulation scenario. So basically, this is the issue we have at hand. If we go to a detailed representation, we'll be facing a very large network. It will be time consuming. In some cases, it's not even feasible under the computer capabilities of our time. Although the other path, let's say this way, if we can find a suitable network equivalent, we will end up with a small network which will be easily implemented in the time domain software, but then we need to be assured that we are representing as accurate as possible all the eigenvalues involved in this equivalent. So we have the issue of the frequency evaluation or the analysis of frequency-dependent equivalence, not only in the frequency domain, but also its transient behavior. One could suggest that we should do a direct fitting of the equivalent nodal admittance matrix of such an area of the system or of the region that you want to calculate the equivalent. But this direct fitting typically will present a poor precision. An alternative to improve the quality of this fitting, it's using something that has been called as mode revealing transformation that improves the observability of the smallest eigenvalues at the lowest frequencies. And we are proposing an alternative approach where we use the idempotent decomposition of the nodal, of the equivalent nodal admittance matrix. We then group in two sets, one dealing with the small eigenvalues, other one dealing with the large eigenvalues. It's important to say that what we are calling small and large with reference to the low frequency behavior, because we know at the high frequency, both part of the networks will present a very oscillatory behavior. So what's the idea of the idempotent decomposition? Given a admittance matrix Y of n, it will be represented by a series of matrices that are associated with the eigenvalues of the original equivalent admittance matrix. Then, instead of fitting each single idempotent, we will group them depending on the behavior they present. Naturally, we have to discuss whether this approach will lead to an accurate response, not only in the frequency domain, but also in the time domain, and we'll discuss this in our paper and in this presentation as well. So the main idea of the paper is to decompose our equivalent admittance in idempotents. So we start with the eigenvalue decomposition. Here we have the eigenvectors, and then we have the eigenvalue matrix. We can rewrite this equation as this, which will lead us to several matrices, M of Y times the eigenvalue Y of I. Just remembering that Ti are the column vectors of the eigenvectors matrix, and S of I are the row vectors of the inverse of the eigenvector matrix. This matrix M of I, it's what we call the idempotent matrix. In a given network, typically we can group these two matrices in one that is related to the open circuit, the eigenvalues associated with the open circuit behavior, and another one dealing with the eigenvalues of the short circuit behavior. So each of these matrices will represent by a set of the idempotent matrices. So if we have the system N, if we have another N of the actual admittance systems, we'll have one group of the admittance going from 1 to the half of its rank, and the other from half plus 1 to the actual rank of the original admittance matrix. We could test the system in several cases. Here we decided to use a case that we think would be more interesting to highlight the suitability of our proposed approach. We We could use to frequency-dependent network equivalent, but in this case, it is not guaranteed that a larger eigenvalue ratio will be presented. As far as we know, representation of a non-uniform transmission line, it's a case where one finds a very large eigenvalue ratio. So it would be a very interesting case to test our approach. Just to remind you that we will divide the group with idempotence in one group associated with the behavior of open circuit currents and the other associated with the short circuit currents. Here, it's our test case. It's one relating to the Amazon River crossing. It's a very tall structure. This is over 300 meters high. Here we have the schematic of the conductors. We see that the tower reach over 330 meters. Here we have the data of the whole system. And this is a twin circuit 500 kV. And we represent the line span. It's over 2 kilometers and 700 meters. It's a very wide line span. And we represent using 35 uniform line in cascade. We use the chain matrix to obtain the overall equivalent admittance, and we consider a frequency range from 0.1 hertz up to 1 megahertz, and we have used 350 samples. Here we have the open circuit eigenvalues, and then we have the ones associated with this in red. We have the ones with the short circuit currents that decrease with the frequency, and then in blue we have the open circuit. It's the blue lines, and we see that they have a very small admittance value at the lowest frequency, and we see that it's a very large ratio. And then at the high frequency, as I said, both systems start to resonate. Just to highlight how by dividing the systems, we can improve them numerically. Here we present the condition number, which is the ratio between the largest to the smallest eigenvalues. And we see the original admittance matrix have a very large condition number, so it has a poor representability. And as we divided in the group with idempotence, we see the condition number has decreased considerably, and we see that regardless if the short circuit idempotent group or the open circuit idempotent group, we see they have a similar behavior through all the frequency range of interest. Then what we have here, it's we subject all of the two sets of matrices to our rational approximations. We have used the well-known vector fitting package, and we have considered both the direct term and the impulsive term and the rational part. One issue of this representation that it's related that one has to consider that passivity should be enforced to obtain stable time domain responses. And the direct fitting, has shown that it has a very, very poor fitting as one would expect. And the one advantage of dividing the systems, and then we can enforce the passivity in each matrix independently. So just to show here, we have the results of the passivity enforcement. When we consider both matrices combined, we see the violation achieves a highest number, and the enforcement is considerably more slow if we enforce them separate, one at a time. Just remember that two stable systems combined together remain stable. So here we have the fitting results. Here for both, those are the actual coupled matrices, grouped matrix, I mean. And here we have the eigenvalues. You see that both the eigenvalues of the original data and the ones obtained with the fitting results have presented a very accurate response for all the frequency range of interest. Just to remind that direct fitting, it's a troublesome approach. Usually one is limited to something around 100 poles. A larger order than this may lead to numerical stability problems. I mean, the passivity enforcement may not find a feasible solution. As we divided in two independent groups, we were able to use 80 poles for each, so it's a 160 poles realizations for the whole systems, and yet we obtain a very simple passivity enforcement. So this is our test case in the time domain. We see we have a step-like voltage at phase at node 1, and then this implies that the whole system is divided in two sets of Norton equivalents. Each one represented use recursive formulation, which is well known. It's been the standard for the realizations of frequency-dependent networks. Here we have the time response. We see that when compared with the numerical Laplace transform, a very accurate response was found. Here we have the output at node 7 and the output at node 10, the induced voltage. Both cases, a very good agreement was achieved. And we reached the main conclusions of our work. Our work has been on the investigation of the idea whether we could group the idempotent decompositions of a given network equivalent and see if it is a feasible solution. To test the system, it was applied to the non-uniform line associated with a wide river crossing. One advantage of this model grouping is the natural separation between small and large eigenvalues. The approach allowed to avoid error magnifications typically found in the simulation response of frequency domain equivalent, and we believe the main contribution of this approach is the possibility of independently fitting the group and enforcing the passivity of each group in an independent form. We thank you, and we are here open to your comments and discussions. Thank you.
Thank you very much. I think now it's time to ask questions. Some of you are saying that you cannot see the Q&A window. It's actually in Zoom. It's you have to push the button and it opens the Q&A window. But if you want, you can ask questions by unmuting your mic. If I can do that for you. Any questions? Xiaopeng, did you have a question?
Hi, Ram. Yes, can you hear me?
Yes, go ahead if you have a question.
Okay. In the presentation, I'm not very familiar with this topic, so maybe this question seems a bit easy. Maybe in the presentation, I see a step is to decompose the admittance matrix Yn into two matrices, and the two matrices have lower rank. That is the YOC and the YSC. I'm not my question is how do you interpret these two matrices? Because I see the speaker says one of the metrics is open circuit like matrix and another is short circuit like. So how is the what is the physical meaning of this decomposition? I mean, what element is open circuited or short circuited?
Antonio.
Hi, Jean. Can I speak?
Yes, go ahead.
Yes. The idea of open circuit would be like you have the response of your systems and you have excited voltage one side and the other terminals are all open. And for the short circuit, it's the opposite situation. You excite one voltage with all terminals remaining short circuit, and then you obtain the induced currents in all the elements. But the idea remains of idempotent is we are just rewriting the whole, let's say, the actual eigenvalue decomposition. So we reach two sets of matrices. The one advantage is to reduce the number of passivity violations as the systems are, let's say, more well-behaved. They have similar behavior, so it will be less of a challenge for the numerical fitting procedure.
Thank you. I have a Q&A question that says, how do they handle similar eigenvalues?
No problem. It will be fitted combined together. The same as we would have in a conventional eigen system decomposition.
Okay. Any other question or we move ahead? I think it's very good. Thank you very much for this presentation. So now we move to the next.